Go. Hello and welcome back to Calculus 3. This is a third section in our integration, multiple integration, and this one is on polar coordinates. So 16.3 double integrals in polar coordinates. So far, to recap, we had functions like this, the top one g, the bottom one h, and then your limits were for f of x, y. Again, let's do dy dx, but you can have the other way as well. A, b on the outside to match the dx, and then we had g of x on the bottom and h of x on top. And these are the two that we covered. Today, we have, so 16.3, we are going to integrate over, let's say, a flower. Something like that. And we are going to deal with the polar domain, meaning r theta. Now, this is the one that will be upgraded into cylindrical and spherical coordinates tomorrow when we do triple integration. So, polar domain is two-dimensional domain where you trace the point by stretching the radius and then swinging the radius on the angle theta that is provided to you. So in case you want to graph a point, let's say 3 pi over 6, you would first draw the radius 3. So you go out 3 units, and then you swing that pi over 6 angle to get to 3 pi over 6. So now our domain can be given in polar coordinates, and we are going to have an integral to calculate the volume. So now the volume integral here of the integral on the region R of f of x, y, dA, right? That we said that's the way we just write this. We are going to have first a rectangular version. Now, rectangular doesn't mean it's a rectangle. Rectangular means just numbers on these sides. Since our integral is going to be the same as in Calculus 2, when you guys had the polar integration in the last section, we had that r d theta at the end. So now you're going to have the function. Your x is converted using r cosine theta. Your y is converted using r sine theta. Those are basic conversions. And here is r dr d theta. Now, this is a string, right, that you memorize as a unit. And you put that at the end of every polar coordinate, including this r. It's not optional. Now, when you look at the limits, the outer limits are alpha and beta. Those are your angles. And the inner limits are a and b, which are your radius r. So say, and this is the formula that you guys use if you have the simplest case. Say you are integrating domain R, region R, is given as the annulus, which is something like this, where this is 2 and this is, let's say, 3. And there is a shape. So think of a pipe, right? Pipe is hollow so that the water can go through the pipe, but the walls have some thickness to it. So if you think about any kind of a pipe, hose, whatever, blood vessel, if you want to work on that, it's fine. All of these things would have the volume that can go through for particular length, which would be given by the z coordinate. So now, if you want to calculate the volume that it's above this ring, we would set up our integral as volume is equal to double integral. Now, whatever your function is, just going to keep this as r cosine theta because I'm just writing out the integral for the limits. Now, what do I have? I want the full circle around, so I'm not looking for a wedge. I'm looking for a full circle around, so 0 to 2 pi, and then I am going from 2 to 3 because that is where the material is, right, where we are looking for volume. So it would be 2 to 3, and this would portray the domain. Then you would plug your function in here and then integrate. So these are the simplest cases, and let's say you want to, so let's take a look at the full example. Say you have what we call elliptical paraboloid. You have elliptical paraboloid. Let's say the height over here is, I don't know, pick whatever, 16. And if it's a circle on the xy plane, right, so it's not elliptical, we would have this equation to be z equals 16 minus x squared minus y squared. So this would be our, right, and if this is the case, it would extend out to 4 and a 4, because square root of 16 is 4. So we would like to find the volume of this. Now, yes, you can set this up in rectangular and shuffle through trig substitutions and all of that stuff, but the polar coordinates make a joke out of this type of a problem. Your project problem that it's due next week, right? One of the project problems is that egg that you guys are supposed to boil and then make, right, trace on a paper, make the get the equation for it, and then integrate. Now, obviously, all of the integration and stuff will be done on a computer. You don't need to type any of the steps because no one cares. We only care about the procedure and those things. When you look at this image here, right, you have a circular base, just like you're going to have with the egg, right? You can think of the egg to be half this shape, not the half, but right, and then the bottom part to be half of a ball, right, half of a sphere. So you can model these very simply using these formulas. So when you look at this, you can transfer this formula easily into your f of r and theta, which is going to be your, well, let's not use f of r and theta. Let's just say f of xy, which are those cosine and sine, and this is 16 minus r squared. That's all it is, because you know from Calculus 1 that your r squared is x squared plus y squared, right? So if you factor out the minus sign, it becomes, right, x squared plus y squared and replaced by r squared. So now I have my function. And if I want to find the volume, I have the double integral. The function 16 minus r squared goes in here. Then I have r dr d theta. I want the full shape. I can cut out a wedge of this if I want to, right? You can cut a wedge, but we just want a full shape, go all the way around. And 0 to 4 on a radius, because the object does not have holes in it, it's just a full solid object. So 0 to 4 would be the radius going from the origin all the way out. So now, when you take a look at this, we have the double integral of 16r minus r cubed dr d theta. And that's what we have. So now, if I have this integral, we integrate the inner integral first. That's going to be 16r squared over 2, so 8r squared minus r to the 4 over 4, computed from 0 to 4. And we still have d theta to work out the second integral. So integral 0 to 2 pi. When I plug in, now try not to compute if you don't have to. Sometimes algebra works out much better. Look at this. You have your 8 times 4 squared minus, and you have 4 to the 4 over 4. 1 4 will cancel. Minus 0, that's all gone. It's very simple to compute this, guys, because this 8 contains a 4 as well. So this is technically 2 times 4 cubed minus 4 cubed, because one of the 4's cancels there. So there's no need to calculate and go into high numbers, because if you have 2 apples and you subtract an apple, all we have is 4/3, 4 to the 3, which is a constant, and we are integrating d theta from 0 to 2 pi. So 4 cubed times 2 pi, which is, I believe, 128 pi, right? 4 through 64 times 2, 128 pi. So we calculate the volume to be 120 pi units cubed, whatever those are. Units cubed, whatever those are. So that's the simplest possible integration for polar coordinates, because it's all of the values are given as numbers, so we call that rectangular. Now I like this problem a lot, like the shape. It's done in a book so you can read it, but if you take a look at this, could be some kind of a tool that would be making holes or cuts, whatever. The edges on top are extremely sharp. Then you have this hole in the middle through which the shavings and excess material can flow through and fall at the other end. So it's a really cool shape. And if you take a look at it, right, the surface z, which is the orange surface, is given as x times y plus 10, right? But that is happening on this circular domain, which contains 2 circles, right? Which we call annulus. And when you combine these 2 together, you get the shape you see. And we can use polar coordinates to quickly come up with the volume for it. Now, it's worked out in a book, so it's worth talking about it because we get to convert stuff. So example 3 in a book. I don't like working out examples that are already done because you guys know all the numbers and letters, so you can read it if you're interested, right? The important aspect here is this z equals xy plus 10 conversion into polar. That's the part that is important. The rest is just plug and chug. So formulas which you guys were supposed to remember from Calculus 2 are the conversion formulas between 2 realms. X equals r cosine theta, y equals r sine theta, and r equals, I can do r squared, is equal to x squared plus y squared, from where r is a square root, obviously, if you want to. So now, since your double integral is technically z r dr d theta, and this z needs to be in r's and thetas, we have to convert our problem into the problem in terms of theta. And we achieve that by replacing x with r cosine theta and replacing the other y with r sine theta, and we still have this plus 10 at the end. So now this becomes r squared, and now you have sine theta cosine theta plus 10. And now here is a $1 million move. You don't want to integrate with these two, sine times cosine, because that would involve u sub. So how about you multiply by 2 and you divide by 2 in front to create the double angle formula, and you create 1/2 r squared sine 2 theta plus 10. So this is much easier to integrate. Much easier to integrate. And now you go and you do that. So that's a really cool trick. Now you can also integrate without doing this, because you can just use u sub, right? You can say u equals sine theta, and du is equal to cosine theta d theta. So you will get sine squared and you go on. It can be done either way, but it's nicer if you are able to simplify, so you don't have to do crazy integration if you don't have to. And let's take a look at one more simple problem, and then we'll take a look at those general regions when we actually get to have functions in our limits. So now this is the integral 24 over region R, where dA is 1 plus x squared plus y squared. And then region R is given as the region R theta, which means that's given as R theta already. R is stuck between 1 and 2. Well, that means it's annulus, right? There is a hole inside. And then theta is stuck between 0 and pi. We are not going the full circle. Now, it is a big deal for you guys to know to graph this domain in polar coordinates. If you need to do this, is to realize, and you can do just the top view, you don't have to do the side view or anything like that. If you realize that you have annulus here, which means those concentric circles like that, but then you also, over here, you only have half of it, because it's 0 to pi, not 0 to 2 pi. So if I want to draw this, I know it's only the upper half. I am going to go 1 and then 2 out, -1 and then -2 out, 1 up, 2 up, and I only get to draw from 0 to pi, so it's only upper half. So this is your domain, and the shape will be on top of this. That's what the domain looks like. Now, clearly we don't, in this particular example, we don't care, but it's good to practice and know how to draw these domains looking at what's given to you as equations here. So now, our volume integral is going to be, let's just put 1 over 1 plus r squared. Because we are using the polar integral, it better be all in r's and thetas. And then I have r dr d theta. Theta is 0 to pi. That's given to us right there. 0 to pi. And the radius is 1 to 2. And yeah, this is easy to integrate. That would be arctangent, but it's not arctangent because of this r. It's actually basic u sub. U is 1 plus r squared. Du is 2r dr, because you do have this r. So you have to use it. So now 0 to pi, and I have my now inner integral changed into du over u, and I need a half. There we go. And I still have d theta. Now my limits used to be a 1 on the bottom, so it changes to 2. And 2 on top changes to 5. So now I can just solve this integral as 0 to pi. And this is 1/2 you can kick outside. We have ln u from 2 to 5, and we still have d theta to deal with. This is 1/2 integral 0 to pi, and we have ln 5 minus ln 2 d theta, which is 1/2 integral 0 to pi. Actually, I can kick this, is ln is just a constant, so ln 5/2 outside. You can combine subtraction of 2 into division of arguments. And now we just need to integrate d theta, 0 to pi, which will give us pi. So pi over 2 ln 5/2 would be the volume that we have on these. So that's that. However, domain can be more interesting. What if you have a flower intersected with a circle, and you are only interested in a volume of a part of the whole thing? Say you have a circle, and then you have a flower poking out like this. Then there is a shape on top of this given by some z equation, and you only want to know the volume above one of these petals. But it's just the part that it's difference between the flower minus the circle. For domains like this, we have to have the general case, because the one with the circle, one with the rectangular one, right, one with the numbers around would not help in this case. So now our integral over region R of fxy dA is going to be given by the double integral of still f r cosine theta, r sine theta. So that's just telling you that you are supposed to convert all of your x's and y's into r's and thetas. Still have r dr d theta, that doesn't change. Alpha beta do not change for limits. Now you have two functions. You have a function g of theta, and you have a function h of theta. So that's what's new. Now, if you don't remember this from Calc 2, then it's a problem. You have to review it. Say you have a domain, let's say r equals 3 cosine theta, and r equals 2. So in this case, you are going to have the picture that I had before. You will have your circle with the radius 2, and then the flower will be poking out to 3. cosine 2 theta, because we have 4 petals. Sorry, cosine 2 theta. Even numbers would double the amount of petals. Odd numbers have the same amount of petals. So cosine of 5 theta has 5 petals. Cosine of 4 theta has 8 petals. So even numbers double, odd numbers stay the same. So now I have that the flower equation here is r equals 3 cosine 2 theta, and I have a circle equation r equals to 2. If I want just one of these difference pieces, well, that piece there would actually go as limits on the integral. And to find those limits, now we have to be careful with, right? So we need to find the limits of integration. The rest we know. There is some function here, and then r dr d theta. So that's never a problem. The issue with the polar integrals here for most of the students is to figure out what are the limits that go on these integrals. You are not looking for the entire flower, therefore you cannot use, since you're not looking for the entire flower, you cannot use 0 and 2 pi. And you clearly have flower function minus the circle function, so flower is going to go on top, circle is going to go on the bottom. So to find theta, thetas, which let's put theta limits. You set two equations equal to each other. So 3 cosine 2 theta equals to 2. From where cosine 2 theta is equal to 2/3. Now, I just made up this problem, so these numbers obviously are going to be terrible, right? But such is life. Hit both sides with the inverse cosine. We have 2 theta is equal to inverse cosine of 2/3. So theta would be 1/2 cosine inverse of 2/3. Now we can actually punch that into calculator and get the values. The values that will come out in degrees, you can turn those into radians if you want to, because we are used to putting these. So let's take a look at, I'm going to change my calculator. Well, it's in radian already. So I'm just going to solve this problem in radian. So let's see. 0.5 times inverse cosine of 2 divided by 3 is 0.42. 0.42 radians. You have to solve these problems in radians because all of the calculus works in radians. Now this means that this angle here is 0.42 radians. That means that the one on the bottom is negative 0.42 radians. And those are your limits. So if you want to calculate the volume, you will have this negative 0.42 and 0.42. The lower function is going to be the circle, so that's 2. The upper function is going to be the flower, which is 3 cosine 2 theta. I didn't give any function here, so just f, and then r dr d theta. Now, for your homework problems and exams and all that stuff, we work out carefully exercises before that, so you don't get to mess with 0.42 radians. That's going to work out to be pi, pi over 3, pi over 2, pi over 4, pi over 6, something that, when you solve the trigonometric equation, you get a nice value for. So when you are dealing with the domains that are crosses between two different functions, you have to use the general case, and this is equivalent to your 16.2 for rectangular coordinates. Because what you have here, if you remember, yesterday we had two different types of function. We have g of x and h of x. We intersected parabola and, let's say, linear line. So we introduced those to the calculation as well. So the polar coordinates work exactly the same way. You either have all numbers, or you might have some of them to be functions. Now, the good part about polar coordinates is you don't switch order of integration, right? So the string r dr d theta is a unit. It's a one thing. It doesn't change into r d theta dr or something like that. So we just have them in this order, so you don't have to worry about drawing messing with the conversions. So now there are a whole bunch of beautiful problems to work with, and some of these problems, as you can see, look like an egg. So it's getting closer to your project. Tomorrow will be the last lecture that you guys need to know for the project to work out those 3 problems that are due on Thursday next week. Modeling the egg could be done using, as I said, half a sphere and elliptical paraboloid, using a circle, obviously. We have a couple of these things. So probably one of the coolest shapes here is problem 38, which I have no clue how would I even draw this thing but I would like to do that problem, because if you understand problem 38, then you understand every other iteration of the problem you can get, pretty much. So for problem 38, we have up is the hyperbolic paraboloid z equals negative x squared plus y squared plus 8. Then we have I squared. There's a hole in the middle with the x squared plus y squared equals to 1. So if you want to work on this shape, the first order of business is to consider its domain, to see how far out it reaches. The good thing is that we want the full shape, so 0 to 2 pi, we don't have to mess with trig equations. But when you look at the shape from the top, you should be seeing something like this with a hole in the middle. And we want the whole shape, because there are no breaks anywhere. Now we know that the inner is r equals to 1. I still don't know what the outer one is, and I will get that when I set these two z equations equal to each other, solve the algebra I have, and then convert everything into polar. So when I set these two equal to each other, negative x squared plus y squared plus 8 equals to x squared plus 3y squared. I will move these two to the other side and get 8 equals 2x squared plus 2y squared, from where x squared plus y squared equals to 4, and that is r squared equals to 4, r equals to 2. So this is r equals to 2 circle, which is really awesome. And now we are supposed to set up the volume integral, where we are going 0 to 2 pi and then 1 to 2 because it has a hole. And now this is why I wrote up and down, or upper and low, or upper lower, whatever. We need to subtract upper minus lower, just like you always subtracted the area between two curves and all of those calculations when you when you're calculating area or volume between two functions. So we're going to have up minus down, and that needs to be done in terms of the coordinates. So I have negative x squared plus y squared plus 8. Subtract that x squared minus 3y squared. I have r dr d theta. I have to clear this algebra and then work out integration. So I have negative 2x squared minus 2y squared plus 8 r dr d theta. We can write this 8 first. It's okay. So 8 minus 2r squared. Because I can factor out negative 2 over here. Let me just do that in blue. If I factor out negative 2, I'm left with x squared plus y squared. And that's the r squared. So that's why it's negative 2r squared. Times r dr d theta, and the integral becomes a joke, because we just integrate 8r minus 2r cubed dr d theta. So integral 0 to 2 pi, we have 4r squared minus, it's going to be over 4, so r to the 4 over 2, from 1 to 2, still d theta, 0 to 2 pi, plug in 2, well that's 16, and that's 16 over 2, so the whole thing is 8, d theta, so 16 pi. So the volume of that object, it's really crazy, awesome shape. The volume is 16 pi units cubed. And the important aspect of this problem is to realize that you have top minus bottom. Maybe I can write that here. Top minus bottom, because you have a shape on top and the shape on the bottom. And it's the same thing going to be with your egg, right? You will have, if you put the egg so it's pointy top up, then you have the paraboloid looking down and the sphere looking up, and then they have to meet at the line. So that's the polar coordinates. The only thing that we added, in addition to what you already learned in Calculus 2, is this inner integral, which deals with an extra dimension that you guys need to calculate the volume. You used to have f r d theta in Calc 2. now we are adding an extra integral inside, which is allowing us to actually calculate the volume. Just be careful what kind of shape in the domain you have, and I hope that you will try homework and bring questions tomorrow so we can address, because you have 3 different things to worry about here. One is the domain, one is solving trigonometric equations if you need to find the limits of integration, and number 3 is obviously trig identities and trig integrals, so you can actually integrate trigonometric functions. Do you know the power reducing formula if you run into, let's say, cosine squared or something like that? Do you know the double angle formula? One that I use the trick to kind of condense, so it's easier. So tomorrow we'll have a review on double integrals, and then after that start triple integrals. Now triple integrals will have 4 different pieces. There will be rectangular integral, there will be general integral, and then cylindrical, and then spherical. So there will be 4 different flavors. We also had 4 different flavors here, right? Rectangular, general, rectangular, polar rectangular, and then polar general. So 4 of those in here as well. And we'll categorize all of that so we'll make sure that you can keep track of everything. Bye.